Our planet, Earth, is composed of different layers of rocks. Its core is a dense mass composed of minerals, gases, and hot molten rock, commonly known as magma. Active volcanoes have a heat source in the Earth's crust, where high-temperature fluids circulate slowly. Rainwater seeps into the continental crust, forming underground aquifers. Upon the water's contact with rocks at high temperatures, a geothermal reservoir is created consisting of hot water and steam. Geothermal energy is generated directly through the power of steam, heated and stored naturally in the subsurface. The steam is extracted through deep geothermal wells drilled into the Earth's crust. Because a geothermal reservoir is pressurized, hot fluids emerge to the surface through faults and fractures in the form of geysers, fumaroles, and hot springs, among other manifestations. The use of this resource for the production of electricity is carried out through drilling of deep geothermal wells to depths of around 1,000 and 3,000 meters until the geothermal reservoir is reached. Geothermal wells have an internal telescopic structure with different diameters and are cased with steel pipes and special cement. Geothermal water and steam are obtained directly from the reservoir and flow to the surface due to underground pressure. Once at the surface, steam and water are separated using a cyclone separator, where the denser, heavier water falls to the bottom of the vessel and steam rises to the top by the effect of gravity. Steam is transported through a network of pipelines, also known as a steam gathering system, to Berlin Geothermal Power Plant. The steam is then gathered in the collector and then flows to the last separation filter for water and steam, called the demister, whose function is to remove the remaining liquid droplets suspended in the steam before it enters the turbine and causes the blades to rotate. For the production of electricity, the turbine rotates at 3,600 revolutions per minute. The rotor of the turbine is coupled directly with a generator, which transforms the rotational energy into electricity. This electrical energy exits the generator and goes to a transformer, where 13,800 volts are converted to 115,000 volts, then delivered to the national electricity grid, and finally transmitted to substations, and from there to houses, factories, schools, and other consumers. The geothermal steam, after completing its function of moving the turbine, goes to a condenser, where it is converted again to water by means of internal cylinders which inject water so steam can be condensed. Once the steam is converted to water, it is pumped to the cooling towers to lower its temperature. Part of the water is used to cool some of the equipment in the power plant, and the rest is re-injected back to the subsurface. Geothermal energy has become a source of abundant, clean, renewable power generation. Reinjection technology recharges the resource so it can be exploited sustainably through a long lifespan. Going back to the wells, the geothermal water derived from the cyclone separator is transported to the binary cycle plant. This machinery uses the high temperatures in geothermal water before it is re-injected to heat and vaporize an organic fluid called isopentane, which has a boiling point lower than water at atmospheric pressure. Once converted to gas, the expansion of isopentane is used to turn a turbine and produce electricity. The main process is carried out through the two systems of heat conduction, which converge at a device called the heat exchanger. Supported by a subsystem known as the cooler or condenser. The hot geothermal water from the wells enters the heat exchanger into a vessel called the reboiler or vaporizer at a temperature of 180 degrees centigrade. In its course through the plant equipment to the reinjection system, the water transfers heat energy to the isopentane, which enters the heat exchanger in the opposite direction to that of the geothermal water. After passing through the reboiler, the water goes through preheaters A and B with a temperature of 160 degrees centigrade. Then, due to further heat transfer to the isopentane, the water leaves the system, ready for reinjection at 140 degrees. On the other side, the isopentane starts its course, leaving the storage tank to a vertical pump, which is sent to the recuperators, where the vaporized isopentane, exiting the turbine, transfers part of its residual heat. Later, it enters the heat exchanger through preheater B and finally to preheater A, where the isopentane receives